So now we're going to deal with the case where the energy level is larger than V naught. So what we're going to be dealing with now is a potential that looks something like this, and this time the energy level is above V naught. So the energy level will be somewhere around here. So let's try to solve the Schrodinger equation, and then our goal here is to find the transmission coefficient. So that's what we're going to be focusing on this video. So in order to do that, let's first solve the Schrodinger equation. Once again, I'm going to divide this setup into two regions. Region 1 for x is smaller than 0, and region 2 for x larger than 0. So in region 1, when x is smaller than 0, the potential is just equal to 0. So the time-independent Schrodinger gives us that the second derivative of xi of x is equal to negative 2me divided by h bar square xi of x. And so we've done this many times before. I'm just going to let this term here be equal to k squared. So that means k is equal to the square root of 2me divided by h bar. And this implies that xi of x is equal to some constant times e to the power of ikx plus some constant times e to the power of negative ikx. So this is xi of x for region 1. And then for region 2, when x is larger than 0, the time-independent Schrodinger equation takes on this form. So this time the potential within this region is equal to V naught. So we plus V naught xi equal to e times xi of x. So with a bit of rearranging, we can dump everything over to the right-hand side. So you see we have negative 2m divided by h bar square e minus V naught xi. So you see that now e is larger than V naught, so this term is positive. So I'm going to group all these terms over here, and then I'm going to call this L squared. So L is going to be equal to the square root of 2m e minus V naught divided by h bar. And so the general solution to this is some constant c times e to the power of ilx plus d times e to the power of negative ilx. And then we're going to be focusing on the scattering problem, where a particle comes from the right, and then it either passes through the barrier and keeps on going, or it bounces backwards. And in such a case, we're going to ignore this term over here. So this is going to be a term that will represent a wave traveling from the right-hand side over to the left. And when we're dealing with the scattering case, we won't consider this term. So all we're considering is this term, c times e to the power of ilx. So in the end, we can summarize what we have so far. So for the region x is larger than 0, our xi of x is equal to some constant c times e to the power of ilx. And then for the region x is smaller than 0, our xi of x is equal to a times e to the power of ikx plus b times e to the power of negative ikx. So you see that this represents a wave traveling from the left to the right. This represents a wave traveling from right to the left. So this will represent the wave that is bouncing backwards. So this will reflect the reflected wave. So in the end, since we're looking for the reflection coefficient in this problem, what we're looking for essentially is the absolute value square of b divided by the absolute value square of a. So that's what we're going to be looking for. So in order to evaluate this term, we're going to consider the continuity requirements. So the first thing we know that is xi of x needs to be continuous at x is equal to 0. So both of these terms should be equal when I substitute in x is equal to 0. So this implies a plus b is equal to c. So you can see that by just substituting 0 inside these terms. So the second thing we need to consider is the derivative of xi of x, that it also needs to be continuous at x is equal to 0. So if you differentiate this, you get ilc e to the power of ilx, and then for this term you get ik a to the power a times e to the power of ikx minus b to the power of negative ikx. So this will be x is smaller than 0, this is x is larger than 0. So when you substitute in 0 and then equal both sides, you get ik a minus b is equal to ilc. So you see that the i's, they conveniently cancel out. So in the end, you can see that a minus b is equal to L divided by kc. So now we have these two equations that we can use, which would help us derive the reflection coefficient. So you see that since a plus b is equal to c, I can actually just take this expression, a minus b equal to L divided by k, and then instead of writing c, I'm just going to write a plus b. And then dividing both sides by a, this becomes 1, so this becomes 1. So in the end, you get something like this. And then I'm going to group the b over a terms together, So I get b over a, L divided by k plus 1. And then for the other term, I get 1 minus L divided by k. And so you see that b over a is equal to 1 minus L over k divided by 1 plus L over k. So essentially you can say that we're pretty much done. All we have to do is that we can square this, and then we're pretty much done. So the rest of this video now is that we need to simplify this expression. So you see that b over a, so now I'm going to multiply the numerator and denominator by k, which would give me a slightly nicer looking expression. And then now I'm going to take the absolute value square of both the numerator and denominator. And since all these terms are real terms, so essentially all we get is a plain old square. And then in order to simplify this a bit, I'm going to multiply the numerator and denominator by k minus L square. And the reason I'm doing this is because I want to have a k square minus L square in the denominator. So this would, when we express everything in terms of E and V naught, so when we express everything in terms of E and V naught, k square and L square would look a bit better than a k plus L. So that's all I'm doing now, is I'm just doing a bit of mathematical trickery to simplify our expression. So here you see we have k minus L to the power of 4 in the numerator, and just reminds ourselves, let's just briefly remind ourselves what k and L are. So let's just write this out first. So if we substitute this into the numerator, you see that k minus L, I'm going to pull out the square root of 2m divided by h bar. In the end, you get a 2m squared divided by h bar to the power of 4. And then inside the bracket, you have square root of e minus the square root of e minus v naught to the power of 4. And then in the denominator, you get k squared minus L squared. So by observing this term over here, you see that k squared minus L squared is equal to 2m divided by h bar square. And then you have e minus e plus v naught. So the e's cancel out, and in the end you get a v naught. So this is k squared minus L squared. In the end, we need to square this. So we get 2m squared divided by h bar to the power of 4. And then we get v naught squared. So you can see that obviously these cancel out. So in the end, all you're left with is, so let's just copy this out. So all you're left with is bracket square root of e minus square root of e minus v naught to the power of 4, and then divided by v naught squared. So this would be your reflection coefficient. So this is the answer to part B.